So thank you all for coming to this part of the conference. I'm going to try not to bring the average quality of the conference down too far, or workshop, whatever we're calling this. So we've talked about the strict tolerant logic and hierarchies thereof today, and that's what we're gonna keep talking about for the next little while. I'm gonna try to build the analog of the strict tolerant hierarchy in the supervaluation, subvaluation setting, and argue that it raises further questions and problems for how to identify a logic. So, background, ST. Well, we've already talked about it a bit, but there is the strict tolerant logic ST, which is defined over strong Kleene three-valued models, and it's a mixed condition consequence relation. So if all of the inference is valid, if at every valuation, if all of the premises get value 1, the K3 designated value, then at least one of the conclusions gets values 1/2 or 1, the LP designated value. So the premises are held to a stricter condition than the conclusions are held to in valid inferences. And so this consequence relation, defined this way, validates exactly the same inferences as classical logic. It is exactly the validities of classical logic. And so one might be inclined to think that it is classical logic. If one takes a sort of Tarskian picture, a logic is a consequence relation. This consequence relation has all the same valid inferences. You might think it's classical logic, but it's not. Because the two logics differ at the level of meta-inferences. So in particular, or most notably, cut, the meta-inference, is not valid in ST, even though it is valid in classical logic. And so that suggests that in order to identify a logic, we can't just look at the valid inferences, we at least also have to look at which meta-inferences are valid. And the Buenos Aires logic group has shown that this same basic phenomenon can be repeated at every level of inference. So they construct a meta-inferential hierarchy. So at the level of meta-inferences and meta-meta-inferences and meta-meta-meta-inferences up for arbitrarily many metas, you can recreate this mixed condition strict tolerant phenomenon and have a mixed condition strict tolerant consequence relation for every level of inference. And they use this to construct logics that have all the same inferences and meta-inferences as classical logic, but differ at the level of meta-meta-inference, and all the same inferences and meta-inferences and meta-meta-inferences of classical logic, but then differ from classical logic at the level of meta-meta-meta-inference, and so on. And this can be repeated all the way through every level of inference, no matter how many meta levels up we go. That says do, it should be go. My apologies. So they use this hierarchy to construct a logic that has exactly the valid inferences of classical logic at every meta-inferential level. So it has all the valid inferences of classical logic, exactly the valid meta-inferences of classical logic, exactly the valid meta-meta-inferences, and so on. And so they argue that this provides a new sort of requirement for identifying or classifying logics. In order to tell whether two things are the same logic, we need to look at their valid inferences at every meta-inferential level. Only then can we determine whether they're the same logic. But Scambler argues that that condition is still not sufficient, that that's not enough. Because he argues that although the hierarchy logic has exactly the validities of classical logic at every inferential level, it is still distinct from classical logic. And he shows that it does not have any anti-validities, in a sense that was defined in a previous talk and will be defined later in this one, while classical logic does. So classical logic has anti-validities, but this strict tolerant hierarchy logic does not. And so the logics are therefore distinct. And so Scambler argues that in order to identify a logic, we need to look at all the validities and all of the anti-validities at every inferential level. And I'm going to argue today that that's still not enough. I'm going to present a logic based on the BPS and Pylos hierarchy, and it's applied in the super subvaluationist setting, and it has all the validities and all of the anti-validities of classical logic at every inferential level. But I'm going to argue that it is still not classical logic. It is still distinct from classical logic. And so I'm going to suggest that looking at the jointly satisfiable inferences, which I will define later in the talk, at every inferential level might be an additional criterion that we need in order to identify a logic. So, in order to go through this hierarchy, or in order to do this, we're going to build a hierarchy of meta-inferences using tools taken from the Buenos Aires Logic Group and some terminology and tools from Scambler's 2020 paper. So let's just start with a normal language. Let's let L be a language. I'm sort of going to assume that we're dealing with propositional logic, but we don't have to. This is general and can apply to any language as long as the language is a set. So we'll call the formulas of the language zero inferences. And so a one inference, which is what we normally mean by inference, is just an ordered pair of sets of formulae. And we can write this as gamma, sequent arrow, subscript 1, delta. So this is the normal sequent arrow from sequent calculi, but now we're subscripting a little 1 because we're going to go to multiple inferential levels, and otherwise it'll get very confusing. So one inferences are just the normal inferences between sets of formulas. Like modus ponens, that's a one inference. Normally we don't have the little 1 subscript there, but here we do. So A arrow B, sequent arrow B. That's an instance of modus ponens. But beyond first level inferences, there are also meta inferences like cut and contraction. And these are inferences between first level inferences. And these we can write using a subscripted sequent arrow like we do with the first level inferences. So a 2 inference is just an ordered pair of sets of 1 inferences. And we can write this as gamma, sequent arrow 2, delta, where now instead of being sets of formulae, gamma and delta are sets of 1 inferences. So sets of ordered pairs of sets of formulae. So we can write cut, and normally we write cut as this sort of sequent calculus style thing with the horizontal line between the premises and the conclusion. But we can write it with the subscripted sequent arrow and sets on either side. And we can do this at every level of inference, including into the transfinite. So we can define a transfinite hierarchy of languages inductively over the ordinals. So at each ordinal alpha, the language L sub alpha will just be the set of alpha inferences. So at our base case, I'm going to stick to propositional logic to simplify things because dealing with quantifiers and identity and whatnot will complicate the picture a lot. So starting with a standard propositional language, a set of propositional constants, and the connectives. And that's our base language. So then given some language, L sub alpha for some ordinal, we can define the successor language as the set of all ordered pairs of sets of members of the lower language, of members of L sub alpha. So for example, L sub 1 is just the set of ordered pairs of formulae, members of L sub 0. L sub 2 is just pairs of 1 inferences, so pairs of members of L1, and so on up the hierarchy through all the successive cases. And then when we get to a limit ordinal, we can just take the union of all of the languages of lower ordinals and throw those into the premises and conclusions. So for a limit ordinal lambda, we can define L sub lambda as the set of all ordered pairs of sets gamma and delta, such that gamma and delta are subsets of the union of all of the lower languages. So as long as we have languages for every ordinal less than lambda, we can define our language L lambda and get a set of lambda inferences.
Can I ask a question here, because there's something I'm missing. The way you've set it up, the language L2 is not a subset of the language L3, and so on up. I mean, L2 consists of L1 sequence, L3 consists of L2 sequence on both sides, and so on. So it's not clear what you're doing with the union here. Each is embeddable into the next one, but it's not part of the next one.
Right. Yes. So at the limit case, we're just taking ordered pairs of sets of members of any of the lower languages, lower ordinal languages.
So you've got the whole sequence with all the subscripts there simultaneously, but that doesn't happen earlier down.
Right. Yeah. And to use Scambler's terminology, the successor ordinal languages are not cumulative, but the limit ordinal languages are.
Okay, that's good.
Okay, good. Yeah. So it might be, in some ways, it might be simpler to have it cumulative at every ordinal, but then that changes what the meta inferences are from what we normally mean by meta inferences, because now formulas can occur. So to keep those cases the same, I'm not letting the successor ordinal languages be cumulative. Only the limit cases are cumulative.
Thank you.
Graham, I can't hear you, but it looks like you're talking.
Yeah, at omega, you've got cross types, which you haven't got up to that point.
I've got what at the
cross types. So you can have gamma and delta of different types. Is that what you intend?
Yes.
Okay.
Yes. Cool. All right. So we can take this induction and define languages that are just sets of inferences for every ordinal. And so for each ordinal, we'll write the ordered pairs that are members of that language as sequence subscripted with the ordinal. So this will give us a transfinite hierarchy of inferences. So for each ordinal alpha, we have the set of alpha inferences, gamma, sequinero, subalpha, delta. And so once we have a hierarchy of inferences, now we need to define notions of validity for each level of inference. So we want a notion of validity for 1 inferences, for meta inferences, or 2 inferences, meta inferences, or 3 inferences, and so on. So the Buenos Aires logic group uses CUNY models like the original ST logic does to define notions of validity, extending the strict tolerant logic ST and using the same sort of mixed condition strategy at every level of inference. So, but here we're going to use a different class of models, and we're going to base it on supervaluation / subvaluation models. So the models are defined over Boolean valuations. So Boolean valuations are just the valuation functions we know and love from propositional classical logic. They're functions from our base language, our set of formulas, to 0 and 1, such that all the connectives obey the truth tables of classical logic. So these are classical valuations. And so an S valuation model, where the little apostrophe there is meant to elide both uper and ub, because supervaluations and subvaluations will both be relevant here. So an S valuation or SV model is a non-empty set of Boolean valuations. And I'm going to use this little mathfrak. I get it by typing mathfrak V, but it looks more like a D and a little bit like a butterfly, so you can call it whatever you want. But that little symbol is going to be the set of SV models. So, and the models are just sets of classical valuations. So on this class of models, or the set of models, a notion of alpha validity is just a function from the models and the alpha language, or the set of alpha inferences, to 0 or 1. So intuitively, a notion of alpha validity tells us which models satisfy which alpha inferences and which models are counterexamples to which alpha inferences. So a model satisfies an inference if the notion of validity assigns that model an inference value 1, and it's a counterexample to an inference if the notion of validity assigns that model an inference pair value 0. So a notion of validity just tells us which models satisfy which inferences and which models are counterexamples to which inferences. So a valid inference, or the valid inferences, are the inferences that are satisfied at every model. Or equivalently, they're the inferences that have no counterexamples. And so when an inference is valid, we'll write this for some notion of validity V as V turnstile gamma sequenaro delta. And an anti-valid inference are the inferences, is an inference for which every model is a counterexample. So valid inferences have no counterexamples. Anti-valid inferences exclusively have counterexamples. And so we'll write this with the reversed turnstile, the sort of turned around turnstile there. So we have valid inferences and anti-valid inferences given some notion of validity. And given notions of validity for some level, we can slice them together to form a mixed condition notion of validity for a higher level. Now, I'm using slice because I got that from Scambler, who in his talk just before this one said he thinks we should use splice now, but I did not, and I agree with him, but I did not consider that until after these slides were made. So every time it says slice, feel free to just mentally replace it with splice, because that does sound better to me. So let V and U notions of alpha validity, or let V and U be notions of alpha validity. The successor slice, so the slice for successor ordinals of V and U, is a notion of alpha plus 1 validity, so a notion of validity for the successor ordinal. Is the notion of validity such that for every model, an alpha plus 1 inference is satisfied at that model whenever all of the gammas are V satisfied at the model, then some delta is U satisfied at the model. So the successor VU slice notion of validity says a model satisfies an inference if whenever all of the premises are satisfied by the V standard of satisfaction, then one of the conclusions must be satisfied by the U standard of satisfaction. So it's holding the premises and conclusions to different standards, just like in ST. We have mixed condition standards for satisfaction. And we can do something similar at the limit slices. So let V sub beta and U sub beta be sets of notions of validity for all ordinals less than some limit ordinal. So we're trying to define a notion of validity for some limit ordinal lambda. And so we're assuming we have some set of premise notions for every lesser ordinal and some set of conclusion standards for every lesser ordinal. So we can write the limit slice of these two sets as the limit slice will be the notion of validity, which this is kind of ugly to look at, but the limit slice will be the notion of validity such that a model satisfies an inference, a lambda inference, if for all the premises, if all the premises are satisfied by the V notion of validity for the appropriate ordinal, then one of the conclusions is satisfied by the U notion of validity for the appropriate ordinal. So if the premise is 3 inference, we look to V sub 3. If the conclusion is omega plus 17 inference, we look to U sub omega plus 17. So whatever lesser ordinal the premise or conclusion inferences might be, we have a premise standard for that ordinal and we have a conclusion standard for that ordinal. And so we can slice these sets of notions of validity at lesser ordinals to get a new mixed condition notion of validity at the limit ordinal. And so given two notions of alpha validity V and U for some alpha, we can build a slice hierarchy over V and U. And we can slice them together in different ways. We can slice V with itself and U with itself. We can slice U with V or V with U and get an infinite, and keep doing that at every level, and get an infinite transfinite hierarchy of mixed condition notions of validity. And so that's what we want to do. We want to slice notions of validity together at every level and get something with all the validities and all the anti-validities of classical logic at every inferential level. So there are at least two interesting notions of zero validity. Sort of, you can think of zero validity as just a notion of truth in a model, because zero inferences are just formulas. So the two notions of zero validity that we can define over our SV models are essentially the notions of truth in a model for supervaluation and supervaluations and subvaluations. So we'll call these P for supervaluations and B for subvaluations. So the P notion of zero validity says that a model satisfies phi if phi gets value 1 at every valuation in the model, which is essentially if phi is super true. So at every classical valuation in the model, phi gets value 1. And B, the subvaluations analog, according to B, the notion of B zero validity, a model satisfies phi, a formula phi, if phi gets value 1 at some classical valuation in the model. So it doesn't have to get value 1 at every valuation in the model. It just has to get value 1 at some valuation in the model. So P is a little stricter than B. P requires that a formula get value 1 at all the valuations, and B only requires that it get value 1 at some valuations. So here are two interesting facts, or I'm not going to tell you what to be interested in, but here are two facts that are relevant to what I'm going to say later. A sentence or a formula is sententially valid according to P if and only if it's sententially valid according to B, if and only if it's sententially valid according to classical logic. Because the only way that every set of classical valuations contains a valuation that assigns a formula 1 is if every valuation assigns the formula 1. And for similar reasons, a formula is zero anti-valid according to P, if and only if it's zero anti-valid according to B, if and only if it's zero anti-valid according to classical logic. So P, B, and classical logic all have exactly these zero inference validities and the zero inference anti-validities. as classical logic. So we might try to build a hierarchy out of those because that looks promising. But as a matter of fact, the hierarchy built over P and B will not give us what we want if what we want is a logic that has all the validities and all the anti-validities of classical logic. Because suppose we take P/B to be our notion of one validity and BP/PB our notion of two validity, which is analogous to the BPS strict-tolerant hierarchy that takes ST to be the notion of one validity and TSST as the notion of two validity. That will have all of the validities of classical logic, but won't have all the anti-validities. Because, for example, the two inference from A sequin arrow 1A to sequin arrow 1A and not A will be classically anti-valid because every single valuation is a counterexample. But it's not BP/PB anti-valid because BP is not reflexive. Because a formula can get value 1 in some valuation and satisfy the B condition without getting value 1 in all the valuations of a model, satisfying the P condition. So there are models that do not satisfy A sequin arrow A, and so this will not be anti-valid. So instead of doing that, instead of slicing P and B together all the way up, we're going to take those as our notions of zero validity and then define notions of one validity directly. And we're going to start with L, which is essentially the local consequence relation in supervaluationism. So a one inference is L satisfied at a model if and only if the inference is classically satisfied at every valuation in the model. So if at every valuation in the model, either some premise gets value 0 or some conclusion gets value 1, then it's L satisfied. So L is essentially the local consequence relation of supervaluationism. But we can define a more tolerant analog to go with it, which I'm going to call M, just because that's the next letter in the alphabet. So the M standard is for satisfaction is that if a model satisfies a one inference if some valuation in the model classically satisfies that inference. So it doesn't require that the inference be classically satisfied at all the models. It just has to be classically satisfied, or at all the valuations in the model. It just has to be classically satisfied at some valuation in the model. So a model satisfies an inference as long as there is some valuation in the model where either one of the premises gets value 0 or one of the conclusions gets value 1. And for analogous reasons to what we saw with B and P, L and M have exactly the one validities and exactly the one anti-validities of classical logic. Because the only way that every set of valuations contains a counterexample is if every valuation is a counterexample. The only way every set of valuations contains a valuation that satisfies the inference is if every valuation satisfies the inference. So they both have all the validities and anti-validities of classical logic. But despite this, M is not transitive. Because even if A implies B and B implies C are both M satisfied at a model, A implies C may not be satisfied. Because the valuation that satisfies A implies B may not be the same valuation that satisfies B implies C. And so there may be no valuation in the model that satisfies A implies C. So we can take a model with two valuations in it, and one assigns 0 to both P and Q, and the other assigns 1 to P and 0 to Q. Well, then the one that assigns 1 to P satisfies the inference from the empty set to P, and the one that assigns 0 to both satisfies the inference from P to Q. but neither of those valuations classically satisfies the inference from the empty set to Q. So the model satisfies the inference from the empty set to P and satisfies the inference from P to Q, but does not satisfy the inference from the empty set to Q. So like the ST notion of one validity, M is non-transitive, yet has all of the validities of classical logic. And unlike ST, M has all the anti-validities of classical logic. So we can use L and M and P and B to define a transfinite hierarchy of notions of validity. So we take our zero case to be L0 equals P and M0 equals B, and L1 equals L and M1 equals M. Those are our base cases. And then at successor ordinals greater than or equal to 1, or given ordinals greater than or equal to 1, the successor ordinal alpha plus 1, L sub alpha plus 1 slices M alpha with L alpha, and M alpha plus 1 slices L alpha with M alpha. So at each ordinal, the M notion of validity defined will be more tolerant than the L notion, because it always has the L on the premise side and the M on the conclusion side. And at the limit case, we just take the union of all of the L's for lower ordinals and use them as the premise condition, and take all the M's for lower ordinals and use those as the conclusion conditions. And then we can define an M sub lambda for limit ordinals lambda. And we can define inverse L sub lambda. And so given these sort of inductive rules for the successor ordinals and limit ordinals, we can define notions of validity for every ordinal. And so we'll call M infinity, the little sideways 8 infinity, the logic that evaluates alpha validity for every ordinal alpha in accordance with M sub alpha. So M infinity uses the M standard, or the M notion of validity, for every ordinal. So at every level of inference, it uses the M notion of validity for that ordinal, for that level. Now, you can prove, I won't go through the proof, but you can prove that at every ordinal greater than or equal to 1, the L notion of validity for that ordinal satisfies an inference at a model if and only if every valuation in the model classically satisfies that inference. So this is the same rule that we applied to define L originally. L at the first level is defined as the notion of validity such that a model satisfies an inference if and only if every valuation in the model classically satisfies that inference. That feature carries on up through the ordinals for every L. And M, according to M at every ordinal alpha, a model does not satisfy an inference or is a counterexample to that inference if and only if every valuation in the model is a classical counterexample to the inference, which is essentially the definition of M we gave at the first level. So that also carries on up through the hierarchy at every inferential level. For every ordinal alpha, a model M alpha satisfies an inference if and only if some valuation in the model classically satisfies that inference. And from this lemma, we can prove that just like at the first level, M has exactly the validities and anti-validities of classical logic at every inferential level. So at every ordinal alpha, M sub alpha has exactly the valid inferences of classical logic, exactly the valid alpha inferences of classical logic, and exactly the anti-valid alpha inferences of classical logic. So M infinity has exactly the validities and exactly the anti-validities of classical logic at every level of inference through all of the ordinals. So is M infinity classical logic? No. It might look like classical logic because it has exactly the validities and exactly the anti-validities of classical logic at every single inferential level. But I will argue, or I think, it is still not classical logic. So for one thing, unlike classical logic, M infinity can tolerate a Liar constant. So I'm dealing only with propositional logic, so I'm not going to worry about trying to put in truth predicates or anything like that. But we can add a Liar constant that gets exactly the same status as its negation at every model. And the strategy is pretty simple. For any model M, any SV model M, take every valuation in that model and produce two new valuations, V prime and V prime prime, such that one of them assigns the Liar constant 1, the other assigns the Liar constant 0. They both assign every other atomic predicate, whatever the original valuation V assigned. And connectives are evaluated according to the classical truth tables, just like they should be in any Boolean valuation. So I'll call the resulting model M star. So for every SV model M, we can convert it into a model with a Liar constant that has the same status as its negation in the model. Both the Liar constant and its negation are sub-true but not super true. So if we extend every SV model M to the corresponding M star, then in our new theory, M infinity will have both lambda and the negation of lambda as sentential validities or 0 inferential validities. And the inference from the empty set to lambda, or the one inference from the empty set to lambda, will be valid. And the one inference from the empty set to the negation of lambda will be valid. So lambda and its negation will both be theorems of the logic or sentential validities. However you want to phrase it. But despite that, we will not have lambda and not lambda. The conjunction of lambda and its negation will not be valid, will not be sententially valid, and the inference from the empty set to the conjunction of lambda and its negation will not be valid. Because no Boolean valuation assigns the conjunction value 1. Every valuation in every model assigns the conjunction value 0. But, or no, not but. In fact, they're not just not valid, they are anti-valid. Every single model is a counterexample to the conjunction of lambda and its negation. And every single model is a counterexample to the inference from the empty set to the conjunction of lambda and its negation. Yet despite this, the inference from lambda and not lambda to the conjunction of lambda and not lambda will be valid, as will the inference from lambda and not lambda to the empty set, or to bot, or to fill in the blank. So even though lambda and its negation are both sentential validities, and the inference from lambda and its negation to their conjunction is valid, the conjunction is not valid and is in fact anti-valid. And hopefully this helps illustrate why I think M infinity is not classical logic. So whereas the inference from the empty set to A and the inference from the empty set to not A taken together lead to triviality in classical logic, They do not do so in M infinity. Classical logic can never have a model at which A and its negation both get designated values, but M infinity can. So although M infinity has exactly the validities and anti-validities of classical logic, there is a difference between the two logics. And following Scambler, I think the part of the difference is that one of them is closed under its valid rules, and the other is not closed under its valid rules. Classical logic is closed under all of its valid inferences, and M infinity is not. So consider the case of adjunction, right? We can distinguish two ways in which a logic might be adjunctive, or it might have adjunction. And classical logic has both. So one way is what I'll call the adjunctive property, which is that for any valuation, if A and B are both satisfied at that valuation, classically satisfied at that valuation, then the conjunction of A and B is classically satisfied at that valuation. So that's one version of adjunction, or one way to talk about adjunction. Another is just the adjunction rule, the inference from A to B, A, B to the conjunction of A and B. And that inference is valid in classical logic. There's also a third option you could talk about, which is that under any language or any signature, if the inference from the empty set to A is valid and the inference from the empty set to B is valid, then the inference from the empty set to A and B is valid. That's another sort of a meta notion of adjunction that classical logic has that M infinity does not have. So classical logic validates the adjunction rule, and it also has the adjunctive property. It also has the property that at every valuation, if A and B are both satisfied, then the conjunction A and B is satisfied. So M infinity validates the adjunction rule, but it does not have the adjunction property. So in a language with the Liar constant, the liar is sententially valid and the negation of the liar is sententially valid, but the conjunction of the liar and its negation is not sententially valid. So it validates the adjunction rule. It validates the inference from lambda, not lambda, to the conjunction of lambda, not lambda. But it's not closed under that rule. It does not have the adjunctive property. So for logic to be closed under its own rules, the valid alpha inferences of the logic need to be closed under the valid single conclusion alpha plus one inferences of the logic. Multi-conclusion is a little more complicated, but at least the single conclusion ones. The valid alpha inferences should be closed under the valid alpha plus one inferences. And the valid beta inferences for beta less than limit ordinal lambda should be closed under the valid lambda inferences, or single conclusion lambda inferences. And classical logic meets this condition, but M infinity does not. And so one explanation for why is that they have different jointly satisfiable sets of inferences. So call a set of alpha inferences jointly satisfiable on a notion of validity if there is a model such that every inference in gamma gets value 1, or every inference in gamma is satisfied at that model. So if there's a model where every inference in the set is satisfied, then that set of inferences is jointly satisfiable. In classical logic, there cannot be a valuation that jointly satisfies the inference from the empty set to A and the inference from the empty set to not A. And so the inference to A and the inference to not A are not jointly satisfiable in classical logic. But they are jointly satisfiable in M infinity. And they can even both be valid, as is the case with the Liar constant. So although the two logics validate exactly the same inferences, they have exactly the valid inferences and anti-valid inferences, they nonetheless have different properties. And one property that they don't share is sets of jointly satisfiable inferences. They have different sets of jointly satisfiable inferences, and they are closed under different rules. And I think they are closed under different rules at least in part because they have different sets of jointly satisfiable inferences. And so they are therefore different logics. But this fact is hidden from view if we look at the logic and if we look only at the valid and anti-valid inferences. If we just look at which inferences are valid and anti-valid, then we miss something about the logic. We miss what rules the logic is closed under. We miss which inferences or sets of inferences are jointly satisfiable. And so in classical logic, the valid inferences are all rules that models are closed under, that valuations are closed under. But that's not the case with M-infinity. So they have all the same valid inferences, but in some sense, the valid inferences or the inferences being valid just mean different things in the logics. They guarantee closure in classical logic. They do not guarantee closure in M-infinity. So I think this shows, or I take this to show, mean that a logic cannot be identified by its validities and anti-validities alone, even taken at every meta-inferential level. So if two logics are closed under different rules, then they are different logics. And if they have different sets of jointly satisfiable inferences, then they are different logics. And it just turns out that having all the same validities and all the same anti-validities at every inferential level does not suffice to ensure that the two logics are closed under the same rules, or that they have the same sets of jointly satisfiable inferences. So two logics with different sets of jointly satisfiable inferences do not necessarily need to be closed under the same rules. So even if two logics agree on which inferences have counterexamples and non-counterexamples, the logics can still disagree regarding which sets of inferences have counterexamples and which sets of inferences do not have counterexamples. So as I think the case of M-infinity in classical logic shows, this will affect which rules the logic is or isn't closed under. If they have different sets of jointly satisfiable inferences, then they can be closed under different rules. And so in order to identify a logic, in order to say these two things are the same logic, or different presentations of the same logic, rather than being different logics, we need at least to consider the sets of inferences that are jointly satisfiable at every inferential level. This is an additional criterion for identity of two logics. So we at least need to know all of the valid inferences at every inferential level, and all the anti-valid inferences at every inferential level, and all the sets of inferences that are jointly satisfiable at every inferential level. And then maybe I think we might be able to identify logics. Right. Thank you.